Good morning, everybody.
Morning, Dr. Terrell.
Hey. I will be right back, everybody. I'm going to grab another cup of coffee. I'll be right back. Good morning, everybody. Let's see.
Good morning.
Morning.
Good morning. Oh my God. What the hell is going on? Why am I cheerful? This does not make any sense. I'm supposed to be friggin' depressed.
It's because you're almost free of us.
That's right. It is our penultimate lecture. Thank you, Vincent. Oh my gosh, life makes sense again. So, what we were talking about. Okay, so first of all, I sent out a memo saying forget about lab 2 and forget about FTIR, and like if I haven't talked about it, don't do it, basically, you know. So so there's not that much left to do. So don't worry about stuff too much. Yeah, I've got to, I don't want to chop up the canvas shell too much because I got to use it next year. It's like, but anyway, so don't worry about things too much. So there's the midterm. We had some homeworks at the beginning. There's no more homeworks. It was the midterm. There's a long report, and then there was a crystal violet report. Then there's UV vis, fluorescence, and Raman. And that's it. We're not going to do anything with the HPLC data. We can talk about it today, but that's about it. Then we've got coming up, we've just got the final exam a week from Friday in the early wee hours of the morning. So, any questions about the class? Yay or nay?
Are we gonna review like the topics for the midterm today or soon?
We can do that on Thursday if y'all want. I think that's probably a good idea. We can do a review on Thursday. And if you want, we can do it during the lab hours that we have scheduled. And I'll be there for lab today, Wednesday and Thursday too. So, Deki.
For the fluorescence lab, it says like on the rubric it has about calculating energy values. Is it something you want us to do?
Oh yeah. There's a page in the lab manual. I am so sorry. That's probably hard to find that out, but there's a page in the lab manual, and it has like a Jablonski diagram where there's the lower energy well and the upper energy well.
Right.
And it's like that, and it's got a few levels in there, right? And then it's actually kind of opaque. So, and then there's these like labels, right?
Mm-hmm.
And the upward is energy, right?
Right.
And then the horizontal is vibrational coordinate. So it's, there's a as many, there's 3n-6 vibrational coordinates. There's a whole bunch of them. This is just one of them, right? And this, so there's really it's really excuse me. It's a greatly simplified diagram, right? And then there's like that. There's these little labels here, and the thing that I'm trying to get you guys to do, and I think basically we've accomplished this right now, is to draw arrows up starting at the baseline there. Go up like that, then start arrows going down from there like that. Good morning, Harry. Daniel. We're hearing the most interesting sort of like slurping and like sounds like somebody's emptying their nose into their microphone. Would that be you, Daniel, or are you, Harry?
I think someone's eating their microphone right now.
I know. I think Harry stopped, but he's still not muted. Maybe I could mute him. Oh, there he is. He's muted now. Okay, cool. So anyway, I just want you to, you could say this is the vibrational coordinate. Then these are the initial states for absorption. And these are the final states for absorption. And then these are the initial states for the fluorescence. initials, and then these are the final states. So that's I want these 6 words, right? And birational coordinate energy, initial, final, and that's what we want on the fluorescence report. Then there's the energy. There's a table of energies, right? And I forget exactly what that looks like. We can take a look at that during lab hours. So I think possibly that would be better. That part should be fairly transparent. Okie dokie. So let's get back on the topic of chromatography here. And so I'd like to bring it back to the idea of improving a separation. Right? We can have a couple of poorly separated peaks where this is signal and this is time. And then we can improve this in either of 2 ways, right? Either we can improve the peak widths. So this is called the efficiency, right? Oops. Figure out how to make this thing settle down here. Or we can, without changing the efficiency, we can change the selectivity so that we still have broad peaks, but it's more selective for the molecules. We could say improve the selectivity, I guess. And the efficiency here, oops. This is given by the Van Deemter equation that we talked about last time. Where the plate height is the badness, and H is equal to A plus B over U plus C times U. And if you can decrease A, B, or C, then you can improve this separation. So this width here, the width is proportional to H, which is equal to A plus B over U plus C times U, where the A is the tortuosity, B is the longitudinal diffusion, and C is the resistance to mass transfer. And mostly what one can work on is A and C. And both of these get better with smaller particles, and both get better with thinner stationary phase. So basically, make the particles smaller. Oops. And make a more uniform surface, make a more uniform stationary phase. Okay, and then to improve the selectivity, what you need to do is you can change the mobile phase or change the stationary phase. Or both, right? So these are a couple of general strategies that you can use to go from a crappy separation. Oops. Oops. To a decent one. Right? Or you could do both of these things. You can improve the stationary phase, you can improve the flow rate, and you could change to a smaller stationary phase with more uniform particles, and then also change the mobile phase such that it selects for the two molecules that you're trying to separate. Okay, this is sort of an overview of the separation problem. Now I want to talk about a particular problem called the general elution problem. Now, there's this is a little bit weirdly complicated here. So, assuming this is the same set of molecules, 1, 2, 3, 4, 5, and 6, right? And you want to separate all 6 of them. So you can do it this way. This is one way you can do that. But you might start here at B, and these are the strongest eluting conditions. And so by strong, I typically mean in reverse phase, Hplc, then the strongest will be the most methanol or acetonitrile. Right? The most organic will elute things the quickest in reverse phase, right? And reverse phase, recall, is the phase where you have particles that are coated with grease. So this is our stationary phase. Okay, go away. This is our stationary phase. It's coated with chicken fat.
Seriously?
Yeah, it's like octadecane is it's a fatty acid, you know. So actually, no, it's not actually chicken fat, but it's probably derived from petroleum. And I'll talk a little bit more about the chemistry, but chicken fat is to get you interested, so you listen and possibly remember what I'm trying to say. But they're very similar, right? And you could use chicken fat literally, but they would hydrolyze off pretty quickly, and then you go from reverse phase and good performance to normal phase and crappy performance pretty quickly. As the like, because the core of this is silica, right? and then the surface is fat. And there's a lot of varieties of fat we can talk about too. There's also aromatic groups, and you can get fancy with it. And usually the columns become more idiosyncratic when you do that. They'll be good for certain things, but shitty for the rest, So there's really no magic bullet, but a very good general stationary phase is just octadecane, just C18. So chicken fat is Si, and then there might be an O, or there might not be an O, and then CH2, 17, CH3. Just all saturated aliphatic hydrocarbon, right? But in any case, back to general elution, right? The strongest eluting conditions, you separate 5 and 6. But you don't separate either of these guys. Right? Then you can go to weaker eluting conditions. So you can cut the methanol. Oops. Cut the acetonitrile. And that causes these peaks to elute more slowly, right? That's pretty good, but still we're not resolving 1 and 2. And then the weakest conditions, we can resolve all the peaks, but peaks 5 and 6, there's 2 problems here. Basically, it takes forever. Which means time, means time and money, right? And the peaks are weak, so they're harder to find. Peaks are broad. Right? So they're harder to resolve and to see. So this is basically a case where we have very highly different K prime values. And it's hard to set the conditions in a single run where you can get all of the peaks to be acceptable, right?
Hey, I have a quick question, Dr. Terrell.
Yes, sir.
So if those peaks are harder to resolve, does that then mean that your information may not be as accurate when you're quantifying it?
Absolutely, yeah. So this simulation here is all set up with the same amount 1, 2, 3, 4, 5, and 6, right? And you can imagine that when there's noise, if this were this had baseline noise in it, then 5 and 6 would be getting closer to non-detectability because of the fluctuation in the baseline. And so, yeah, it totally affects accuracy and precision, all these other questions. So, you always want a sharp peak that's well resolved from baseline and from other peaks, so it's got to be resolved left and right and up and down. So very good question, right? So, oops. I think I spilled onto another page there. So this is one way to state the general elution problem is that if the solvent is weak enough to separate 1 and 2, then separation takes too long for 5 and 6. And 5 and 6 broaden into the baseline. And if separation is strong enough to elute 5 and 6 in a reasonable time, then 1, 2, 3, and 4 co-elute, and they're not separated. Yeah. So what is generally done is gradient elution, right? And in liquid chromatography, this means you start with a weakly eluting conditions, right? In LC, this is the weak. You could start with mostly weak solvent. And then finish with strongly eluting conditions. Then you go to mostly strong solvent. So let's just review real quickly what in liquid chromatography what this looks like. So and there's two different cases here, and I'll use them in general. And I don't know how to say this. So let's look at two cases. There's reverse phase. We've got chicken fat on octadecane on silica, right? And in this case, the weak solvent is water. Say H2O, and then the strong solvent is methanol. And then for normal phase, this is reverse phase. And then for normal phase, we have particles that are terminated in OHs mainly. Then the weak solvent is going to be hexane. And the strong solvent is going to, again, be methanol. So let me just make this slightly more intelligible here. Right, and so when you have the let's start with understanding why water will be a weak solvent when you have an octadecane stationary phase. Who would like to take a shot at explaining that? Do my job for me here for a minute. Matthew?
I'm sorry, I didn't hear the question.
Why is water a weak solvent in reverse phase as opposed to methanol, which is a strong solvent?
Give me a second. This is something I should know.
Yes, sir. So weak. Go ahead.
Oh, I was just gonna say, is it weak because a lot of the things that you're trying to elute are organic compounds?
Yes, yes. Everything that we're trying to elute now is an organic compound. That's right. That's a good point. This type of chromatography we're talking about is all organics. And generally, normally not even ions, but just organic molecules. So weak means things are retained. The weak solvent promotes retention. And the strong solvent promotes elution. Right?
Could it also be because water has a dipole? It's both polar and nonpolar, whereas the other one is just.
You started perfect, Catherine. Started
polar?
Perfectly. Water is just polar, and methanol is both polar and nonpolar.
Oh, so it's the reverse. My bad.
Exactly. No, but that's perfect. It's a perfect place to start, right? So the weakly retaining, water is weakly retaining because there's the greatest contrast between the water and the stationary phase, which is a completely nonpolar.
Does it also depend on the solvent that you're using? Because most solvents dilute faster than the others.
So the contrast that I'm drawing now is between different solvents, right?
Yeah.
And solvent number 1 is water. Solvent number 2 is methanol in reverse phase, right? There's reverse and normal. Normal uses no water, but let's focus on reverse for right now, because reverse phase is much more commonly used. And outside of synthesis, right? For synthesis, you do a fair amount of normal phase stuff, but in the analytical world, reverse phase separations are the norm. And in reverse phase, water is the weak solvent, right? Because when you dissolve a bunch of things in water and you put them onto this column, they're going to have a choice between dissolving in the water and dissolving in the chicken fat, right? And as you add more methanol, things will come out of the chicken fat and into the mobile phase, into the liquid phase, into the solvent phase. Does that make sense? I'm sort of not actually speaking in such general philosophical terms as I'm sort of telling you how it works. You know, I mean, when you do reverse phase, generally what you're talking about, you need somewhat nonpolar solutes, right? If you have all polar solutes, then reverse phase will not work, right? If everything you're trying to separate is completely hydrophilic, right? They're not going to partition into the chicken fat. They're all just going to elute. So in reverse phase, water is the weak solvent because the analytes will be retained. And then you can use methanol to cause things to elute. So this is the methanol is what promotes the elution. Now, it's a good point now to contrast this with normal phase, where the stationary phase is actually the polar phase of the two. And the mobile phase is hexane. I'm going to rewrite that here. Hexane, right? It's so now you have this great contrast between a very polar stationary phase and a very non-polar mobile phase. So in reverse phase, this is non-polar. And this is polar. And then in normal phase, this is polar. And this is non-polar. That makes sense? So when you use normal phase, your weak solvent is hexane because your analytes are polar. You know, actually, that's a third column I've got to put in here is analyte type, right? Gosh. Okay. Forget that for now. But in both cases, methanol is the strong solvent. So methanol is the strong solvent. Think of methanol as sort of like a universal solvent here. It's got a polar and a non-polar part to it, right? And it will pull things off of the reverse phase column, will also pull things off the normal phase column. Okay, so the way that you use that in gradient elution, right, is that you start with the weakly eluting conditions. So, and finish with the strongly eluting conditions. So, let's see how I do in terms of. So let me actually give some examples of that. I'm going to go here and say Control Enter, get us a new page, and then say, well, in reverse phase, there's a. Let me tell you an interesting story here. At least it's interesting to me. Hopefully, it'll be interesting to you. My wife used to work at a mill. It was a place called NanoSyn. NanoSyn. There's a NanoSys, which it used to be a startup too. I don't know. They're probably a lot more sort of tame now. But NanoSyn is it's an organic synthesis place, right? And they have good organic chemists. And what they do is they take contracts from the pharmaceutical companies to synthesize libraries of compounds. And they have to work really fast. They charge a lot of money, and they work really fast, and they develop synthetic strategies. And they have to be better at this than the chemists that work for the pharmaceutical companies. So that's where their entire bottom line is, right? And Mitra was, she was doing the separations for everybody. She was always running these concentration gradients. And she would start with 100% water. Right? That's where she would start. And then she would, over time, move to 100% acetonitrile. And then, it might be, 80, 20, 50, 50, 20, 80, and then 100% acetonitrile, So there'd be a gradient in the eluting conditions. And the reason that they did this was that they needed to get everything off the column and start before they started the next run. So 100% acetonitrile is a good solvent system, and normally that would dissolve everything that they were shooting onto this column. But this is a very extreme gradient, And it was kind of wasteful because they used a lot of acetonitrile. But they had to do this because had to get their column cleaned out every time. They had to elute everything that they put in, and so they would use these fairly extreme gradient conditions, and and a lot of times, by trying to dissolve everything in 100% water, things would precipitate on the column, and the column would clog, and they'd have to replace the column. So it was kind of a dodgy way of doing things, but it worked for them. And this solved the general elution problem that they had, because they always had these bad mixtures. They had these very difficult mixtures, and they would be doing separations at different stages in the synthesis. So they had to know how many components were there, and where they were and how polar, and what was going on at every stage. So they used gradients that started with 100% water and ended with 100% acetonitrile. So this, this idea of beginning with a weakly eluting and finishing with a strongly eluting conditions worked well for nanosyn, and unfortunately not so much for my wife, because she changed jobs. She went on to work for Chevron. She's been there for I think about 15 years or something like that. Yeah, but it's coming up on 15 years, I think. But she does mostly synthesis now.
So, Dr. Terrell.
Yes, sir.
How common is it to go from 100% water to 100% acetonitrile? Because those seem like pretty extreme.
Yeah, and the truth is that I don't know. I know that, for example, when I was working up the conditions to do Coke and coffee and stuff like that, I never needed to use a strong solvent gradient, because all of the components were water soluble, right? So I just had to tease them out, with about 40% organic. So in that case, I'd use 60% water, 30% methanol, 10% acetonitrile. And I would just run those conditions, and that was plenty of selectivity and to get everything that I needed off the column. Now, if I were doing synthesis, and I had, some starting materials that were more organic in nature. Let's say I was trying to do some dodecane thiols with amino head groups, right? And there was a lot of possibilities in this. They could be making disulfides, which would be much more hydrophobic. And in that case, I would need, I would prefer to end with 100% acetonitrile, but I might have to start at 50% acetonitrile, because in those cases, as things get very hydrophobic, you do need more acetonitrile or methanol. And I'm sort of talking in circles now, because I'm not really a separations person, but I've sat through about 50,000 Joe Pesek seminars, and so I get it, and I've had intersect with it a little bit, but I think it's fairly unusual to do it in this extreme of a case. Now, you might say, well, why not just always do a solvent gradient like this? It makes perfect sense. You can get everything out at the end and be ready the next time. The reason is that it actually, when you start this, you start at 100% water, and then you end at 100% to start the next run, you have to go back here, right? To the start. And then, you know, so at the end, you can basically, you can say the percent ACN, right, versus time. And you can go, well, we're going to go, right? Say 0 to 100. And then at the end, you can go back, right? Well, the trouble is you can't just start again. You need to equilibrate at 100% water again. So this equilibration time is important. And so there's when you run a gradient, you do need a fairly substantial equilibration time at the 100% water end, because it just doesn't work otherwise. I mean, solve that problem. That's a good problem to solve. I mean, maybe you can just, you know, somehow microwave the column or something, you know, at a really high pressure, high temperature, and sort of like get all the acetonitrile out, but it takes a while. Somehow the solvent gets trapped in these tiny pores in the stationary phase. And it just takes, you know, a good 15 minutes of flow to get it all out of there. So anyway, so this is the equilibration. So let's look at an example here. So there's oh yeah, there's also baseline drift, right? So you have to choose a wavelength where there's not, you know, there's not much UV absorbance for either of the solvents, right? Because sometimes what will happen is as you go to from one solvent to the next, the baseline will just keep drifting up and up and up, and you get like, you know, you'll get this drift up here. So this is the drift. But and then the equilibration time is another problem that I mentioned earlier. So let's just look at an example here. In GC, because GC is it's actually the easiest way to do temperature programming, and it's normally how it's done. And if you have a mixture of compounds here, and you try to separate them at low temperature, then the column, there's still a lot on the column. After 30 minutes here, right? So this is never going to work, you know. Then you can go to 145, and you lose a lot of resolution. For the poorly retained components, or the low boiling components in this case. But if you start cold and you slowly get hot, then you can basically resolve everything. And this is always, for GC, it's always a good approach. You know, unless you're real extreme, you have all really light things, or all really heavy things. But generally, for GC, you can, over time, right? There's time, you can change temperature along the same axis, and then this gives a great separation. So this is solving the general elution problem in gas chromatography. Does that make sense, everybody? The general elution problem? Okay. So now let's talk about some qualitative aspects of HPLC here. And there's a nice nomogram here. It's as old as the hills, but it still applies. There's you can think about the molecular weight of the solute, and you can go from small molecules to polymers and biomolecules. Say proteins, etc. And biomolecules. There we go. And then you can also talk about the polarity of the aniline, right? So biomolecules are probably going to be over here. Right? Because, I mean, not all of them, obviously, but like for, let's say, DNA bases, polynucleotides like DNA and RNA, they're going to be in this end, right? So let's say DNA and RNA, the longer ones, right? The larger pieces, right? And so for DNA and RNA, we use basically a mode of separation called gel filtration. And the most common mode of gel filtration is called PAGE, for Polyacrylamide Gel Electrophoresis. And basically you run these guys through a gel using an electrical current, and it is so amazingly efficient. It's just amazingly efficient at separating DNA bases. It just blows my mind when I see the ladders that are produced by PAGE experiments. But there's one way, right? And then you can talk about the nonpolar stuff. This is reverse phase territory here, you can reverse phase is called a partition type chromatography, right? Come on, you. And partition because in reverse phase there's actually I don't have enough real estate here. Hold on. Oops. In reverse phase here we have our surface. We've got carbon, 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 carbon. Then we've got molecules in here which partition into and out of this solvation environment. You know, you can imagine this guy being some aromatic job. And then, so this is solvated by the stationary phase. This is solvated by the mobile phase. And so, and then there's normal phase here. So this is RP. And then NP is, it's also referred to as, I would actually refer to normal phase as an adsorption phenomenon. But I'm not really sure about this, but the normal phase here would be and then we'd go from let's see here. And this is the stationary phase. This is in the mobile phase, right? So this is normal phase. Right. So here's the normal. Right. And then there's also, you know, I really do not know what fucking is referred to there, honestly. Ion exchange and GPC, I understand here. GPC is for mostly for synthetic polymers. And we'll talk about the mode briefly. Right? And then ion exchange. Ion exchange here is for literally for any type of ion. And let's talk about what that is. So here's what we went over earlier. Weak, strong, retained, diluted, right? Reverse and normal phase, right? Then exclusion is where large molecules elute more quickly. That's kind of funny, isn't it? And then in page, large molecules are actually retained. Right? I'm not going to go into the mechanism. I don't really understand it that well. And then in ion exchange, basically the stationary phase is ionic. And so the, it can be, or it could be quaternary ammonium groups, Oops, I'm not C. N CH3 3 plus, right? You can have a permanent cation exchange or anion exchange. This is a cation exchanger. It's like think of it as well, it can take on temporarily any number of different cations and sort of bind to them weakly and then let them go, And then this guy exchanges anions. So because it's got a permanent cationic sites, And so there's a whole world of ion exchange chromatography. We're not even going to touch on it here. But so that's basically all of the chemistry I'm going to talk about for HPLC. Let's talk a little bit about the instrumentation. This this schematic has been true for many years here. But basically, you have solvent reservoirs, and oftentimes they are degassed. And they used to degas them using helium, but I hope that's not done anymore because that's a terrible waste of helium. But the yeah, see, there's a helium source there. Yikes! Not anymore. Hopefully, they use actually vacuum now. They pump it through semi-permeable or gas permeable tubing, and they put the tubes under vacuum, and they can pump the gases out. But then they'll have the solvents could be water, methanol, acetonitrile, even acetone in reverse phase, and then there'll be a solvent proportioning valve or pump combination, right? And the idea is that you pump, I think mostly now they're proportioning pumps. And so you set the pumps to be different amplitudes. They can be anywhere from 0 to a large amplitude, right? And so you can make any proportion of these solvents that you want. You can go from 100%. This is A, B, C, and D. You can have 0 to 100% of any one of the 4, or any combination therein. And and then you just basically put it through an injector, and then oh, sorry, this is a primer. This is not exactly what I was talking about. Then there's an injector here, and then there's a column. This is basically all. The only one that's sort of important here is a filter, and an injector, a column, a detector. So so the injection valve is clever. I thought I wanted to share that with you a little bit. There's the valve is this body. It's literally, it always is circular, and there's 6 ports on the valve, right? There's the outside, and then the inside, right? And the inside has these little loops here. And then when you twist this guy a little bit to the left, then the solvent stops going this way and it starts going this way, right? It's either just sort of bypassing the stupid thing, or then it goes like that, you know? And so either you're running through this one or you're running through these two, depending on the position this valve's in. So you can quickly shift this between these two positions, right? And so this is called the load position. Because when the valve's in this position, you can put your sample in here and fill this injection loop. Right? And then when you're ready, you simply switch the valve to the left. And then you're in inject mode. Right? And then you just let it inject until the solvent loop empties, right? Then you go back to load. So you go load, inject, load. So the timing diagram might be like load, inject, load, inject, load, you know, and then you've got your separation that's going to happen here.
And this is a method to give you a consistent volume of your sample?
Exactly. Thank you so much, Matthew. I completely forgotten that. But yeah, this avoids one of the major problems in chromatography, which is the variability in the injection volume. And so this largely, well, it helps that, you know. So thank you. Yes. You can tell that Matthew's actually done this as a job, you know. And I've never done this as a job. My experience is mostly teaching this class. So I'm not an expert.
The I used was a lot different than the one that you're describing, though.
Yeah. Did you have a one of these 6-port valves?
No, actually, we had just one, and it was it would go in the injector would go through a tube, and the tube was specially manufactured to have a certain volume in it.
Mm-hmm.
And then that would it would suck up the sample and then inject it into the basically into the solvent stream.
Yeah. I bet you it was one of these.
It may have been.
I think it probably was. From what you describe, it sounds like this exactly, you know, because you know you've got it in load position, right, and it's just running, right, and then at that point you have a needle that goes into the vial, and then you've got a syringe that pulls it out. There's a syringe. And then you just pull so much of this stuff out that you completely fill this loop, right? And then boom, then you switch it back. and then you empty it out, right?
Yeah.
It could have been one of these types of valves. So who knows? Who knows? It's just a clever design. It's been around forever, but
well, I can tell you it was a Varian Pro Star, and it was like the Millennium Falcon of PLCs, because
exactly
broke down like on a daily basis. So if
and
anyone out there needs help,
but wait, that makes you Chewbacca.
does that make? Well, I don't know about that.
Either that or you're Han Solo.
Because if I'm Chewbacca, then who was my Han Solo?
Okay, cool. Maybe you were Han Solo. Somehow I see you as Chewbacca.
Well,
Okay.
I am known to tear arms off when I lose.
There you go. There you go. You are definitely Chewbacca.
But yeah, so if anyone out there needs help troubleshooting an HPLC, I'm really good at it.
Excellent. Excellent. Cool. Yeah, on the job training. Okay, so let's see, where are we here? So this is basically oh, okay. So I'll let you look through. A lot of this is kind of retrospective. You know? There's the most common type of detector is UV vis. This is what we used. There's refractive index and light scattering. And these are more general, but somewhat less sensitive. This is slightly limited. But sensitive. And then mass spec is when it works, it's when it's good, it's very, very good. But when it's bad, it's horrid. You know? Who's that little girl? Who knows this? Who knows this one? Matthew, do you know it?
Wait, what? When it's bad, it's horrid? What?
Right. There was a little girl who had a little curl right in the middle of her forehead. And when she was good, she was very, very good. But when she was bad, she was horrid. So this is the little girl detector. They are, when you can get an LC with an MS together, it's amazing. Sensitive and general. Super informative. But these things are idiosyncratic and they can be horrid. Because they work about 10% of the time in our experience. And then every time you put something new in there, you've got to optimize the solvent systems. So LCMS is just wonderful, but it's very idiosyncratic and it can be a big pain in the butt. Okay, guys, so I think that about wraps it up for today. I tell you what, let's draw a line here in terms of what we're going to cover. And so I think that's it for the class. Yeah, that's fine. Up to here. And I'll make a note of myself when I write the exam, when I rewrite the exam, to stop there. And then on Thursday we'll review, and I'll try to give you an overview of what we're going to cover on the final. And to preview this, the final will be 1 week from Friday in the wee hours of the morning, starting at 7:15 and going on as long as you can do it. I don't think it's going to be hard at all, but if you don't, if there's parts that you haven't studied, there might be some blank spots for you. It's going to be in 2 parts. And part 1 is completely optional. You do not have to take part 1. Part 1 is a resurrection for the midterm. So if you did crappy on the midterm, you're like, damn it, I know I could have done better, then you can take part 1 of the final. If you just leave part 1 blank or you do crappy on part 1, most likely you're going to keep your midterm score. If you ace part 1 of the final, then that ace score will then replace your midterm score. All right, so part 1 of the final is a resurrection for the midterm. Part 2 of the final will cover the last half of the class, topics in the last half of the class. And I'll give you problems, problem sets and whatnot to work for practice for these guys, okay?
Yes, please.
Yes, please. Excellent. Problems are coming. Problems are coming. Solve problems. Okay, guys. I will, yes, I'll be back. Yes, sir.
So what's the deal with the HPLC lab and the other lab?
Just canceled.
Okay.
I'm not going to do them. Just don't try, because I'm not going to grade anything on those, and so don't worry about them at all.
Wait, Professor, what about the other 3 labs? The ramen and the fluorescence.
They are all due. They're open, and there are YouTube videos on my channel.
But due today, or due today, right?
No, they're due actually. I think it's a week from today.
Okay.
No, a week from yesterday. It's the last day of classes.
Okay.
So try to get them in as soon as you can, but they're actually due on the last day of class.
Yeah, I'll get the report into Professor. I kind of neglected to give you the long report.
I know.
Yes.
You're not the only one, my guy. So.
You guys are bad.
Yes.
Hey, I
Bad,
turned in more
bad.
stuff over the weekend.
Good. Excellent.
So Professor,
Yes.
For the
Muting
fluorescence, for the fluorescence, it says write a short paragraph indicating the procedure.
Oh yeah, just forget about that.
Forget about that. So
sorry about that. Yeah, sorry.
So do the calculations and
right.
Explain
the graphing and the calculations. That's all you got to do. Yep.
Okay.
Exactamundo. Sorry about that.
Well, just don't forget to like and subscribe.
There you go. Don't forget to like my channel, my incredibly boring YouTube channel, on which this will appear later today. Alrighty, guys.
And lab at 10 today for those who have Tuesday.
Yeah. I'll be there at 10 o'clock today for anybody who wants help with anything.
Dr. Carroll.
Yes, Catherine.
What so I know you ended at 17.12. What did we start on? Is it 10?
Oh shoot, I'm not sure. You mean for the final?
No, for the when you started lecturing.
Today?
No, when you started lecturing for the
After the midterm, right?
yeah, after the midterm.
Yeah, I'm not sure right in this second, but I'll put that stuff together for you for Thursday.
Okay.
Okay, cool. Good question.
And I want private office hours with you.
You want private office hours? Okay, good. Excellent. Yeah. So if you want them today, I can do them today from.
No, not today. Maybe another day.
Okay, just email me. Just email me.
Okay,
Anybody
because
who
I'm
wants.
gonna work on the lab
Yeah.
report.
Okay. Good.
Okay.
Excellent.
Bye.
Okay. Bye-bye, everybody.